All right, a couple more examples of solubility product Equilibria problems. First one here, solid silver chromate is added to pure water, 25 degrees C. We're told some of the solid remains dissolved at the bottom of the flask, right? So that means it's at equilibrium. The mixture is stirred for several days to ensure that equilibrium is achieved between undissolved silver chromate and the solution. Analysis of the equilibrated solution shows that its silver ion concentration is 1.3 times 10 to the minus fourth. So there's some information about the system at equilibrium. Right? And what we want to calculate here is KSP. So first, we're going to need the equation. So if we start with silver chromate, solid, you should recognize that when that dissolves, it's going to break into two silver ions, plus one charge for each silver ion. But then chromate, being a polyatomic ion, that stays together in aqueous solution. So one chromate ion. Now what we know from the problem is once we get to equilibrium, the concentration of silver is 1.3 times 10 to the minus fourth molar. Now from the stoichiometry of the reaction, we should be able to determine what the concentration of chromate is as well, since all of the silver in solution is coming from dissolution of the silver chromate, and that's also the source of the chromate ion. If we're getting two silvers every time one formula unit of silver chromate dissolves, but only getting one chromate, then this concentration has to be half of this concentration. So at equilibrium, the concentration of chromate would be 0.65 times 10 to the minus fourth molar. Right, so I just divided 1.3 by 2 there, right? And it's not quite the way you'd normally write scientific notation, but it makes it easier to see that it's just half of that concentration. Now, from there, to figure out the equilibrium constant, solubility product constant in this case, we just need to plug into the equilibrium constant expression. So KSP here for silver chromate would be the silver concentration squared, again, don't forget that 2 up there in the balanced equation, times the chromate ion concentration. And we've got both of those now, so we can just plug those in. So 1.3 times 10 to the minus fourth squared times 0.65 times 10 to the minus fourth, and that will be our KSP. So if we multiply all that out, we get 1.1 times 10 to the minus 12th. And that would be the solubility product constant for this particular material, silver chromate. Okay, excuse me. Second example here on the page, we're asked, will a precipitate form when 0.1 liter of 8 times 10 to the minus third molar lead nitrate is added to 0.4 liters of 5 times 10 to the minus third molar sodium sulfate. Right? And a little bit of a hint here, we're given the KSP for lead sulfate. Now, this essentially is a Q problem. We're trying to figure out if the reaction is going to shift in a direction that would give us solid. And from the information provided, this is the reaction we should be interested in. Lead sulfate dissolving would give us lead in solution and sulfate ions in solution. Now, if this equilibrium shifts back toward the reactants, then that means solid is going to form when we mix these two solutions together. So we can solve for Q here and see if Q tells us the equilibrium would shift forward or backwards in this particular case. So QSP here would be concentration of lead times the concentration of sulfate, right? And we have no coefficients in our balanced equation, so we don't need any exponents here as well. But what we do need here are concentrations. We've got two solutions, we mixed them together, the volume is changing, so our concentration is changing as well. So let's calculate what those concentrations are. Now for lead, we start with 1/10 of a liter. The molarity of the lead is 8 times 10 to the minus third moles of lead nitrate per liter. Now there's one lead ion per every one formula of lead nitrate. So this calculation could be for lead nitrate or for lead ions, but since we're interested in lead ions, that's what we're trying to figure out here. Now, this would mean there's 8 times 10 to the minus 4th moles of lead in this solution. The volume now has changed. It was 1/10 of a liter, but since we added the additional 4/10 of a liter, this is 1/2 of a liter total volume. So divide 8 by 0.5, that would be 16, so this becomes 1.6 times 10 to the minus 3rd molar for a concentration of lead. We can do a similar calculation for the concentration of the sulfate ion. Again, there's 1 sulfate in every formula of sodium sulfate, so we won't need to change from the original molarity. 0.4 liters of sodium sulfate solution, 5 times 10 to the minus 3rd moles per liter from the given molarity of the solution, and that gives us 2 times 10 to the minus 3rd moles of sulfate ion. Divide that by the volume of the solution, 0.5 liters. So 2 divided by 0.5 would be 4. So 4 times 10 to the minus 3rd molarity of sulfate ions. Now we can come back over to our Q expression here and just plug in those concentrations. So QSP in this case would be 1.6 times 10 to the minus 3rd. For the lead, 4.0 times 10 to the minus 3rd. For the sulfate, multiply that out and we get 6.4 times 10 to the minus 6th for Q. Right now, if we compare that to the KSP that was provided, 10 to the minus 6th, that's a larger number than 10 to the minus 7th. So in this situation, Q is greater than K. If Q is greater than K, that means these concentrations are going to have to end up lower as we approach equilibrium. For these concentrations to get lower, that means our equilibrium's got to shift back in this direction. So some of the soluble ions will have to turn into the solid, and that means solid will form. So we have enough of a concentration to push the equilibrium backwards and form some solid or some precipitate in this solution.